The Bell's spaceship paradox, a seemingly simple thought experiment, unveils the intricate and often counterintuitive nature of special relativity. It presents a scenario where two identical spaceships, connected by a taut string, undergo identical acceleration, leading to a clash between classical intuition and relativistic predictions. The resolution of this paradox underscores the fundamental principles of length contraction and the relativity of simultaneity, demonstrating how our everyday understanding of space and time breaks down at relativistic speeds. At the heart of the paradox lies a seemingly straightforward premise. Two spaceships, A and B, are initially at rest, joined by a string capable of withstanding immense tension. They then simultaneously, according to a stationary observer, begin accelerating in the same direction with identical magnitudes. Classical intuition suggests that since both spaceships accelerate identically, the distance between them should remain constant, and therefore the string should remain intact. However, special relativity paints a different picture. Relativistic analysis reveals that both the spaceships and the string undergo length contraction as they accelerate. While the observer witnesses this contraction, the crucial element lies in the rate of this contraction. The acceleration introduces a disparity in the rate of length contraction experienced by the string compared to the distance between the spaceships. This difference, though subtle, accumulates over time, causing the stress on the string to increase. From the perspective of the spaceships, they always measure the same distance between them, but the string, according to the spaceships, must stretch. This ever-increasing tension ultimately leads to the string's rupture. The resolution of the paradox hinges on the relativity of simultaneity. Events deemed simultaneous in one inertial frame are not necessarily simultaneous in another. Though the spaceships accelerate simultaneously in the observer's frame, they do not do so in their own instantaneous rest frames. The rear spaceship, B, experiences a slightly greater acceleration in the instantaneous rest frame of the front spaceship, A. This seemingly minor difference, accumulated over the duration of the acceleration, causes the distance between the spaceships to increase in their own frame, effectively stretching the string. This paradox serves as a powerful illustration of the limitations of classical intuition. It compels us to abandon our ingrained notions of absolute space and time in favor of the relativistic framework, where length contraction and the relativity of simultaneity play pivotal roles. The Lorentz transformation, the mathematical foundation of special relativity, provides the tools to accurately describe the relationships between measurements made in different inertial frames, offering a consistent and accurate description of the universe at high speeds. In conclusion, the Bell's spaceship paradox is more than just a mental exercise. It is a profound demonstration of the counterintuitive nature of special relativity. By exposing the flaws in our classical assumptions, it illuminates the fundamental principles that govern